Next is the reference electrode. The reference electrode, that is an electrode whose potential is known to us and it is used to determine the potential of some other electrode. For example, suppose I wanted to know the electrode potential of the potential of this particular electrode. Let the electrode is a zinc. This is the zinc electrode, which is placed in a zinc sulfate solution. That is a metal-metal ion type of electrode. And I just wanted to know its potential. That is, I just wanted to know the E0 value of zinc. We have the electrochemical series, and in electrochemical series we have the values of all the electrodes, and those all values are determined first for the given electrode. So suppose in the same way, if in the electrode potential they had given the value of zinc electrode potential also, but the question arises that how they measure the value of that zinc electrode. So here we are learning, or we are doing that, how to measure the electrode potential of a given electrode. So to know the electrode potential, see, E0 of zinc, that means it's a potential I have to determine. So to get the potential of any electrode, it is clubbed with the another electrode. So I linked up, it is linked up with the other electrode. Let this electrode is R, which is placed in a solution of R, and there is a galvanometer which will measure the cell potential. We are forming a galvanic cell where the chemical energy is converted into electrical energy. This is your salt bridge, I can say. Okay, now this is the reference electrode R. This is an electrode whose potential is already known to us, means its value is known. My aim is to get the value of the zinc potential, the potential of the zinc electrode. Now, how to get the potential of a zinc electrode? Once whole setup is done, the reaction will start by its own, depending upon the standard potential of the zinc and the reference electrode. The one which will have the higher oxidation potential will oxidize, and the one which have the higher reduction potential will reduce. Okay, so finally the reaction will start, and after that some electricity will be generated, and that electricity is measured with the help of this galvanometer. So we measure the cell potential. So here the cell potential, suppose I got the cell potential as a 1.5 volt. That is standard cell potential. It is a 1.5 volt I got. Okay. Now to get this 1.5 volt, now if I'm making a formula for the cell, that is E0 cell, how E0 cell is equal to, the formula will be E0 of cathode minus anode. Let R is a cathode and the zinc is an anode. Here, as I said, R value is known to me. How much it is? Let it is minus 0. Or plus 0.82. So this value is known, it is 82, and the zinc potential is to be determined here. And the E0 of cell, we got it this value as a 1.5 volt. So I can say that E0 of zinc is equal to 0.82 minus 1.5 volt. And this will give you the value that is 0.68 volt. So finally I got the value for the zinc potential. The zinc potential, that is 0.68 volt. It's just an example. The actual value of a zinc is 0.76. Just an example that I got 0.68 volt. So this is a way how we measure the potential of any electrode. So this R electrode which is used here, the zinc electrode, it is the one whose potential is to be determined. The R is an electrode whose potential is, why we are using this R electrode which is used to get the value of zinc and whose potential is already known, is called as a reference electrode. So here the electrode R is called as a reference electrode. So whenever I want to measure electrode of a potential of one electrode, any electrode whose potential is to be determined. So to get the value of this potential of this electrode, it is clubbed with the another electrode whose potential is already known to you, and whose potential is known to you, and it is only used to get the potential of this. Then this electrode will be called as a reference electrode. So reference electrode is the one whose potential is known, and it is used to get the electrode potential of some other electrode. Now here we have the electrode. So the first reference electrode potential which we have is standard hydrogen electrode. that is SHE, standard hydrogen electrode. Standard hydrogen electrode, that is SHE electrode, is considered as a primary reference electrode. Now, what is primary reference electrode? The primary reference electrode is an electrode whose potential is just assumed. See, for example, suppose the first electrode whose potential was to be determined. For getting the electrode potential, we should have at least one reference electrode. So, suppose that first electrode whose potential was to be determined, and the potential of that electrode, for getting that potential of that first electrode, we again for that also we require the one reference electrode. Until that time, there was no reference electrode. So, there is a one electrode whose potential is to be assumed and is called as a primary reference electrode. So, here the standard hydrogen electrode is a primary reference electrode whose potential is not calculated, but it is just assumed, and on the basis of this assumed value of this SHE electrode, the potential of the other electrodes are calculated. So, here we have this as a primary reference electrode, and there is only one primary reference electrode, and all the electrodes which are used other than SHE, they all are considered as secondary reference electrode whose potential is determined by using this SHE electrode. So, primary reference electrode in this, let's see the arrangement for this. The solution contains 1 molar H plus ion, which we get by dissolving HCl or H2SO4 in a water. Here we are passing hydrogen gas, pure hydrogen gas. Under a pressure of 1 atmosphere. Platinum electrode. Here the platinum is acting as an electrode and it is an inert electrode, I can say. And this platinum electrode is coated with the platinized platinum. Platinized platinum or black platinum, it is a coating is done only to provide the large surface area. Here the reaction which is taking place, it takes place on the surface of this platinized platinum. So, the rate of reaction will depends upon the surface area. So, it is coated with the platinized platinum only to increase the surface area so that the more reaction will take place. So, in this case, I can say that the electrode which is used, it is an inert electrode, that is a platinum electrode. Then next, the electrolyte which we have here is 1 molar H plus ion solution. We are passing a hydrogen gas in this case, and then the standard, as I said, standard hydrogen electrode potential is assumed. So, E naught of SHE, that is standard hydrogen electrode, is considered as 0 volt. It is assumed as a 0 volt, that is standard hydrogen electrode. Then it's a representation. How it is represented? Then it's a representation is for writing it is a single electrode, and for writing a single electrode, first we write its ions and then electrode. But as I said, in addition to ions and electrode, if there is some gas or salt which is taking part in a reaction, then we mention that gas or salt also. So here we have a hydrogen gas which is taking part in a reaction. So representation of electrode of SHE. It's a H plus ion whose concentration is 1 molar. Then hydrogen gas we are passing, and the pressure is 1 atmosphere. And then platinum which is acting as a inert electrode. So this is a representation of SHE. Now the standard hydrogen electrode may act as an anode or it may act as a cathode. So if it is acting as an anode, whether it will act as an anode or cathode, it depends upon the electrode potential of the other electrode. If that other electrode's reduction potential is more than this, then other electrode will, that is, if the other electrode's reduction potential is more than 0, then that other electrode will act as a cathode and this will act as anode. And so here it acts as a cathode as well as anode. So if SHE act as a cathode, then what reaction will take place? If it is acting as a cathode, then on cathode the reduction takes place, that is a gain of electron. So I can say that H plus will gain electron, the reaction will take place between these two. One will act as a reactant and other will act as a product. So H plus will gain electron and will form H, but as we know that H is always diatomic, so 2H plus will gain 2 electron. So it's a reduction. And if SHE act as an anode, if it acts as an anode, then exactly the opposite reaction will take place, that is the oxidation will occur, that will be a loss of electrons. So the reaction will be H2, which gives exactly the reverse reaction, 2H plus plus 2 electron. This is oxidation. Whether it is undergoing oxidation process or reduction process, it's a value, that is electrode potential is going to be 0 volt. This SHE electrode comes under, or it is a type of, I can say we had learned about that there are total 4 types of electrodes. So SHE comes under a gaseous electrode. This is also known as hydrogen gas electrode, where H plus ion is solution and the same gas is passed, that is a hydrogen gas. Now how it works? Suppose if I just wanted to know the electrode potential of this particular electrode, this is the electrode whose potential is to be determined. So I will use a salt bridge between these two. This is the salt bridge, and both of them are connected with the help of metal wire. There is a galvanometer. I just wanted to know this electrode potential of this electrode M. So, and the solution is containing the same M plus ion solution. So the formula will be, I know that SHE electrode potential is 0, that is E naught of SHE. The formula will be, just start the process, you will get the some cell potential value. Here I got E naught cell is equal to, suppose I got 1.5 volt again, or 1.8 volt let. So formula will be E naught cell is equal to, it's oxidation, this is acting as a cathode suppose, or it is acting as an anode, let it is acting as an anode. So the formula will be E naught of M minus E naught of SHE. E naught of cell is 1.8 volt, electrode potential of N we have to determine, minus E naught of SHE, standard hydrogen electrode is always 0. So ultimately I can say that E naught of M, it is equal to 1.8 volt. So with the help of SHE we can easily calculate the electrode potential of any electrode whose potential is not known. So SHE is considered as I said, it is a primary reference electrode. But while using SHE, there is some problems like SHE. In case of standard hydrogen electrode, we have to use pure and dry hydrogen gas. The hydrogen gas is highly inflammable gas, and getting a dry hydrogen gas is again a very difficult task. And the use, as I said, hydrogen gas is a highly inflammable gas. So the use of that hydrogen gas is again a dangerous one. Then here continuously we are passing a hydrogen gas inside the solution. The solution concentration is to be maintained as a 1 molar. So when dry hydrogen gas is added, then that hydrogen gas start absorbing some water molecule, that is it absorbs the solvent, and due to which I can say that evaporation takes place and that the solvent quantity goes on decreasing. And if the solvent will decrease, then maintaining a concentration exactly 1 molar is again a difficult task. And then third is that it's a maintaining a pressure of the hydrogen gas continuously 1 atmosphere. So these are some limitations of hydrogen gas electrode. So every time for getting the value of every electrode, instead of using a standard hydrogen electrode every time, we use some other electrode, and those other electrodes are called as a secondary reference electrode. So now let's see, after the standard hydrogen electrode, let's start with the secondary reference electrode. The next is a calomel electrode. The calomel electrode, which is considered as a secondary reference electrode. So it is an example of a secondary reference electrode. and it comes under metal sparingly soluble salt electrode. That means it is a metal sparingly soluble salt electrode type. Metal sparingly soluble salt electrode is the one where the electrode is covered with the salts and which is placed in a solution which is containing the same anion which is present in a salt. So let's see the calomel electrode. So calomel electrode, this calomel electrode, first it is filled with the mercury. So at the bottom there is a mercury liquid. This mercury liquid itself is acting as an electrode here. So this mercury is an electrode which is covered with salt. So this is covered by its salt, that is a mercurous chloride. Hg2Cl2, and then it is filled with saturated KCl solution. This is the side tube which again contain KCl, and end of the tube is packed with the cotton or some glass wool. And mercury being an electrode, it is like there is a one platinum wire which is immersed here, and it should undergo still mercury, because mercury is acting as an electrode, and that electrode where the electron is lost or gained. So with the help of this platinum metal, this electron transfer is done to the other electrode. Now while using a calomel electrode, it's a one advantage is that there is no need of using a salt bridge. Because this side tube itself acts as a salt bridge, we will see that how it acts as a salt bridge. Okay, then calomel electrode, as I said here, the electrode is a mercury. Covered with its salt, Hg2Cl2, and kept in saturated KCl solution. Now when I am talking about the electrode potential of calomel electrode, the electrode potential of a calomel electrode depends upon the concentration of KCl. It depends on concentration of KCl. How? For example, suppose if I am having the concentration and E naught value. If you have 0.1 molars concentrated solution, then say electrode potential is 0.337 volt. If it is a 1 molar, then its value is 0.280 volt. And if you are considering saturated KCl, then its concentration is 0.242. Means as the concentration increases, that E naught value goes on decreasing. So here the electrode potential of the calomel electrode totally depends upon the concentration of the KCl solution. So by changing the concentration of KCl, we can change the electrode potential of the calomel electrode. That's so here I can say that it is the value of electrode potential value is reproducible here. Now let's see the representation part now, the representation of electrode. Representation of electrode. So here we have Cl minus ion, that is a solution, and after that the electrode comes. Here the electrode is a mercury, and but in between there is a salt, and that salt is taking part in a reaction, so you have to mention that salt also. So mercury, Hg2Cl2, and then mercury in a liquid state. Here the Cl minus ion, that is it stand for the solution, but I know that Cl minus ion is always a KCl. Here we always use KCl. So either use like this, or instead of Cl minus I can write KCl also, because it's a fixed electrolyte, Hg2Cl2 and then Hg. We can use any of these two. Like a SHE, this also act as a anode as well as cathode depending upon its oxidation potential with respect to the other electrode. So if calomel act as an anode or act as a cathode, suppose cathode means reduction will take place. Reduction means Hg2Cl2, which is a salt, will gain electron, and after gaining electron it will produce H2Hg plus 2Cl minus. And if it is acting as an anode, if calomel act as an anode, then exactly the opposite reaction will take place, that is 2Hg plus 2Cl minus, that is the oxidation will occur, and it will give you it will produce Hg2Cl2 plus 2 electron, that is the oxidation occurs. Now how it works? So suppose this is a reference electrode. As I said, there is no need of using a salt bridge, because this only acts as a salt bridge. So this is another electrode whose potential is to be determined. And it is connected here. This is a metal electrode M placed in a solution of the same ion. KCl is acting as an electrolyte of the salt bridge also. So now the reaction will start, and suppose for reference, let here the solution is a saturated KCl, and if it is a saturated KCl, then its E naught value is 0.242. if I am considering the saturated, then only. Then E naught, suppose I wanted to know the value for this. So just after, once the whole thing is set, the reaction will start by its own, and some electricity will be generated, and we measure its cell potential. Let E naught cell, I got 2 volt. So I will use a formula to get the electrode potential of this. E naught cell is equal to, let it is a cathode, so E naught of M minus E naught of calomel electrode. E naught of M, which we have to calculate, this is 2 volt, E naught of M. Calomel electrode value is 0.242. So E naught of M, I can say it is equal to 2 plus 0.242. That is equal to 2.242 volts. So like a standard hydrogen electrode, this can also be used for knowing the value of the electrode potential of any electrode. And since its electrode itself is known by using a hydrogen, that's why it's a secondary reference electrode. Its value is not assumed, but it is this electrode potential for the calomel is calculated, or it is determined experimentally, and so it is considered as a secondary reference electrode.